All right, let's finish up that proof for the record, phonograph record, a disk of charge, and then finding the electric field at point P. All right, now we left off the other day, and we finally got it down to this form of it after we did the integration. So now we've actually got to put the numbers through. So let's see what we actually have here. All right, so I actually prefer the half in the bottom. I've changed that, and then I put a 2 up in the top. So instead of dividing by half, I just put a 2 up in the top, so that took care of that. So that's what this is all about. The minus sign in the bottom, I just moved that out in the front here so that we end up with a minus sign, and that's due to this minus sign here. Our boundaries still go from R, which is the size of the disk, from 0 all the way out to R itself. So nothing's changed here. Now, when we start to actually apply the boundaries, 0 and then R, well, our first term, obviously, we're going to replace the little r with a big R, which is the actual radius of the disk. So when we plug that in, we end up with this, fine. And then we plug in 0, we end up with this, because isn't the R going to disappear when we put the 0 in? Well, it still leaves us the z squared in the bottom, so we end up with the square root of z squared. Well, let's clean this up a little bit. I think that, some obvious things here. Can we cancel out the 2 and the 4 and just have a 2 there now? And then same thing here. We've got the 2 and the 4. So we cancel the 2 out like that, and we're left with the 2 in the bottom. All right, now, what is the square root of z squared, you say? Well, it's z. And then we have a z in the top as well. So this is z, and the top, z in the bottom. We can cancel these out. So the z goes away in that term only, though. All right, so let's see what we end up with here. Now that the 2 is canceled out with the 4, we end up with a 2 in the bottom. Still have a minus sign. The z is still present. And we have the square root of this. We've got to put the square root sign, and it kind of looks like that. Kind of nice. All right, then over here, there's not much left. I have a minus and then a double minus. So a minus and a minus make a plus. All right, and then we end up with sigma in the top, 2EO, and then everything else is crossed off, so we end up with this one little term here. All right, now let's rewrite that one more time. So when we look here, we've got E, that's the electric field strength itself. Would you mind if I put the positive term in the front? That's what most people are going to do there. So I've got sigma divided by 2 epsilon naught, and then minus sigma, we've got the z there, 2 times epsilon naught, and then times this quantity 1 over the square root of z squared plus r squared at this point in time. All right, now let's factor out, since we got sigma 2EO, and we got sigma, and then there's another one, 2 epsilon naught. Let's factor that out. So we got sigma 2 times epsilon naught. All right, now if we multiply it to try to keep this thing, if I distribute it out, isn't that times 1? So we're going to end up with a 1 here. All right, now we factor this out, so we get rid of the epsilon, the sigma and the 2EO, so that's out here in the front. And then that only leaves us in the inside part. That's going to end up being just the 1 over square root, z squared plus the r squared. It kind of looks like that. So let's double check ourselves. Sigma divided by 2 epsilon naught times 1 is this. Sigma divided by 2 epsilon naught times this is going to end up that. So one last thing we've got to worry about, we've got to have that z up in the top, so make sure you have the z right there, and that kind of finalizes it. Not much else we could do with that as far as I can see. All right, now this would be our final answer. So when you're doing your proof, make sure that you have something that has the form of something around like this. All right, now, the next question is, what would happen if the disk is really, really big? So I start out with this nice little phonograph record, and it has a radius of big R. Nice. All right, now what happens if I make this big R larger and larger and larger? So if I really think about it, can I make this plate infinitely large? So we're talking about a plate that is just huge. All right. Now it's very difficult to draw an infinitely sized plate, so it's just kind of a thought experiment. It doesn't have to be round anymore because basically it's going to take up all the space. You know, it's just going to keep going and going. Now let's look at the consequences of that in this formula here. So as r gets larger and larger, what's actually going to happen in this particular situation? Well, as this gets larger and larger, we're going to end up with a situation where this approaches, as r approaches infinity, like so. Isn't this denominator going to get really, really large? All right, so if we do that, this is going to get larger and larger and larger. So we're going to end up with, here, actually end up with a 0 term. So as this gets huge, this is going to become as of 0, like the way it should be. Now 1 minus 0 is just 1, and then 1 times that is going to end up being sigma divided by 2 epsilon naught. So what is the electric field strength for an infinite sheet of charge? And the answer to that is sigma divided by 2 times epsilon naught. So we've got another friend. Now remember, this is a special case where the r value is so large, we've got this huge sheet. All right, so for practical purposes, you know, you can't really produce that, but we know we can get things that kind of approach that. So if the sheet is relatively large, this does come out to be true.